I went over some of the homeworks that were just due, and the quizzes. And let me address some of the issues as we're doing this example. Okay, but there are a couple of things that will make your life much easier if you keep track of. So, let's see. I'm just trying to think. Yeah, okay. So we're going to look at a neural network, and we're going to do we're going to first do forward propagation, and then we're going to do backpropagation. I was just filling out the weights here. So let's look. V2 is 0, W3. Okay, this is what I've got so far. I've pre-calculated it, but if my numbers don't turn out right, I reserve the right to change my final B at the end so I can get whatever number I want. How many levels in this, or layers in this neural network? 3. So let's look, actually. Here are inputs. Which layer is this layer? 1, 2, 3, and this is actually 4 going over to our loss. So what's coming out of this one here? Y hat, right. What's another name for this? It's the output layer, which is the 4th layer, right? So therefore, we know if we kind of look at the left side of this and the right side of this, the left side of this is named what? Summation. It's a summation, but we normally give it like a z, right? So we say z at 4. And then applying the activation function, we get what? A at 4. Y hat's just another name for A super 4. Okay? And similarly, these are going to all have names too, right?
So is A super 4 a function or a vector?
As I'm showing it right now, it's a vector. It's our value. We can look at this in more than one way. We could look at the function that's being computed, or we could look at the output. Right now, I'm sort of looking at it as the output. Okay. What else do we need to know to completely define this? We need to know what our activation functions are. So our first 3 activation functions are going to be ReLUs for these layers, and the last activation function is going to be a sigmoid function. If we look at our loss here, what would be a good loss to use? Cross-Entropy. Right. The cross-entropy works well with probabilities. The sigmoid outputs a probability, so that would fit. Okay, and we know the form of this, right? The minus y log y hat plus 1 minus y log 1 minus y hat. All right, so let's go through and do some computations. I'm not going to make you come up to the board to do this. Let's not do it this way because I find the matrix way so much easier. So let's start. What do we want to compute first? Anyone? And I'll help. This is called the forward pass, right?
I just think that you want A of 0.
Okay, so A of 0 is what?
X.
I guess we need that, don't we? X equals, so as far as our computation, we can't do anything without an X. All right, so x is 3, 5. Another name for x is? A0. Yeah, so A0 equals x equals 3, 5. Next thing we want to compute, or the first thing we want to actually compute. A1 is good, but we need something before A1 because A1's on the right-hand side of the node.
Oh, sorry,
Z1. Yep. So Z1 equals A0 matrix multiplied with W1. Okay. We look at the layer. This is layer 1. We need the outputs from the previous layer plus these weights. Morgan.
Don't we also need the
Let's throw in a B. Is that what? Yes. It's plus B at 1. So this equals 3, 5 for negative 2 plus, it actually is an array, negative 1. So it equals 12 plus negative 10 is 2 plus negative 1 equals 1, which matches what I calculated. Now we can calculate Nick's A1. A1 is going to be what? It's going to be 1 because what's our activation function? ReLU. So, right? It equals ReLU of Z at 1 equals 1. Now we can calculate C2 equals A1 W2 plus B2. So 1. What is it? Negative 521. First day, I have forgotten to start the video going. So, well, actually, it's red. Maybe I did start it. How do I know? I will stop it and start it and see. So hold on just a second. Okay, it made a noise. All right, it was working. Plus something seems wrong about this. What's wrong about this? What's wrong about this is that's not my W2. Okay? My W2 is going from 1 to 3. So therefore, it's a 1 by 3. This is a 3 by 1. Let's fix it. So, why did I do this? To check whether you guys were awake. So, what were my numbers again?
Negative 5, 2, 1.
Negative 5, 2, 1. Okay. What should this guy look like? Same by 3. Same thing, 1 by 3. So this is going to be 0, 0, 0, let's say. Okay. So that'll equal negative 5, 2, 1. A2 is equal to the ReLU of this, right? What will change? Well?
So that will be 5, 1, 5, 2, 1.
Because?
0,
0, 2, 1. Right. And let's hope I'm still on track in my numbers. I'm still on track of my numbers, and finally Z3. Well, actually, it's not really finally, because we have 2 more layers. So we have, and I'm going to start putting these numbers, right? 0, 2, 1. The matrix we're going to use is W3, which looks like the right shape, doesn't it? 1, 1, 1, 2, 1, 2, plus negative 1, negative 2, equals, and we want something that looks like this. 0, 2, 3 plus negative 1 is 2. 0, 2, 2 is 4 plus negative 2 is 2. Plus negative 1 is 3. Because I know where I'm going. Right, and then finally, I'll come over here. Z4 equals, what is the array? 2, 3?
Yeah.
Times a matrix? 2, 3 plus? What is it?
Negative 13.
Negative 13? All right. I actually just can't see it, so I'm really asking you for real. So that's 4 plus 9 is 13 plus negative 13 is 0. How convenient. Because when we compute A at 4, we're not doing ReLU anymore, we're doing sigmoid. And the sigmoid of 0 is 0.5. Okay? So that's sigmoid of 0 equals 0.5, right? And this is applying the sigmoid across all of its inputs. So if this were a output with a layer 3 here, or a size of 3, then we'd be doing the sigmoid on each one. And we'll end up with a sigmoid of the first element, sigmoid second element, sigmoid third. Does this one make sense? All right. What's our loss equal? What's y? 0. So therefore, the first term, the y log y hat, goes away, right? So we're left with, right, so we have 1 times log of 1 minus y hat, right? Equals log of 1/2. We'll throw in a negative there to be right. Equals, what's that?
I think it was
0.69. All right. Let's say that. Any questions on this? All right. Just as a suggestion for your midterm, you will want to be able to do forward propagation. Yes?
I'm just a little bit confused on the matrix addition.
Yeah.
Getting to 2, 3.
This one here?
Yeah.
All right. So we're doing a row times a column here, right? 0 times 1, 2 times 1, 1 times 1 gives us 3.
Yeah.
So this little matrix here is going to be 3, and 0 times 2, 2 times 1, 1 times 2. So that's 4. 3 plus 3 is 2. I'm confused too.
It's 2 plus 4.
So it's 2 plus 2 is, you're right, it's 4. Somehow I was doing 2 plus 1, which is craziness. So 2 times 1 is 2, 1 times 2 is 2, that's a 4, plus negative 1, negative 1. Does that make sense?
Yeah.
Okay. All right. Now we're ready for the backpropagation. We have seen that if we want to figure out, for instance, the derivative of this weight here, that we need to know the derivative of the loss with respect to this here, right? And that will, in order to calculate the derivative of this loss, we're going to calculate the derivative of every path, right? The multiplication of the individual derivatives along every path for the loss. So if we were to go to here, we would need to go from the loss to here, to here, to here, and also from the loss to here, to here, to here. And that would give us this loss, which can give us this final. Yes? Does that make sense? But if we were to go back to this weight, we've got a bunch of paths that we need to traverse. And so we don't like that. So we are going to keep in mind, let's say we needed to calculate this weight, okay, the derivative with respect to this weight. We would go from, and let's look at this node in particular. So we go from here to here, to here to here, from here to here, to here to here, from here to here, to here to here. How many times do we go through this? 3 times. Do we need to calculate this loss 3 times? Why don't we just calculate from the loss to here 1 time and then just use it and store it from then on? Okay. And similarly, once we've calculated the loss from here to here, store it and never ask again. So this is dynamic programming. Right? Dynamic programming is just a problem that has repeated subproblems plus a cache, or memoization. So dynamic programming equals a problem with repeated subproblems plus memoization. And yes, it's memoization, not memorization.
Is it
Well,
equal to that thing that you have it equal to up there?
Dynamic programming equals this.
Just wanted to make sure that.
Yeah, that's a good point, because we just have a sequence of equals there, so that'd be complicated. All right. Often in dynamic programming, you use an array, and you kind of work your way in a certain order through your subproblems. You don't necessarily have to do that. You could always just have a memoization. It just says whenever you calculate one problem, save its result, and just make sure to use that cache value again. But it's often easier to go through in a certain order. And in our case, the order we're going to go through, given its term to backpropagation, is backwards. So we go have our forward pass, and we did layer by layer by layer. And in fact, within a layer, we did Z and A and Z and A and Z and A. And now we're going to just work our way back the other way. Okay, so we're going to compute the partial derivative of the loss with respect to A4, the loss with respect to Z4, the loss with respect to A3, with Z3, with A2, with Z2, with A1, with Z1. And from those Z's, we can then get the derivatives with respect to each weight and each bias. Does the plan make sense? All right. So we need some approach to do this. Let me keep one. So here's what I know we're going to need to do. We're going to need to store these A's and Z's in order to make this work. We'll need our weights. We need our picture. So we're going to have to figure out where we can do our work. And I guess we will do that. That's our Z4s. We're going to move over here. So excellent. We can see that part of the board. So we know the partial derivatives. We know the single step derivatives. So we know the derivative of L with respect to A4 is just depends on our loss function. You know, we looked at the cross-entropy. We know the derivative of A4 with respect to Z4. Okay? Because that's basically the sigmoid. So we know L with respect to y hat. Except I don't want to write this derivative for this particular problem. All right? For this particular problem, the derivative of the cross-entropy is a little bit messy. We also do know the derivative of y hat, which equals a4, with respect to z4. In fact, why don't I just get rid of the y hats and call them a4. What's that equal to? It's a sigmoid, right? So we said a4 equals sigmoid of z4. So the derivative is sigma prime. So the derivative with respect to z4 is sigma prime of z4. But what's the derivative of sigma prime? Well, in this case, if it's x, sigma prime of x is sigma of x times 1 minus sigma of x. Okay? So this would be equal sigma of z4 times 1 minus sigma of z4. But what's sigma of z4? What is sigma of z4? a4. So this equals a4 times 1 minus a4. And we basically did something similar to this on the homework, right? Last week's homework. And we saw something nice that happens when you put this derivative multiplied together with this derivative. What did we end up with? Y hat minus y. So if we say, let's not look at these two separate derivatives, the derivative from L to A4 and the derivative from A4 to Z4. When you have cross-entropy and a sigmoid, work with them together because it's such a pretty derivative. So we're not going to even go to A4. We're going to go directly to Z4. And that equals y hat minus y. Okay, now if you have a different activation function at the end and a different loss function, you may want to do them separately. But whenever you have sigmoid and cross-entropy loss, take the derivative of them together. Questions on that point? So that would have made your last quiz and homework much easier.
Do we have to derive this every time, or can you just know?
You just know it.
Okay.
Yeah. You got to do it in your homework, and now you can say, as I've already shown. All right. So we know that. Next, we're going to move on. So in the general case, this is our specific case here with this particular activation function and the loss function. In the general case, if we have, let's say, from a at I, the derivative from a at I to z at I, we have some activation function at that layer, right? The activation function is g to the I. We would take the derivative of that, evaluate it at z at I. So that is the second equation here. So the first equation says we know the partial derivatives of each step along the way. Partial L with respect to partial y hat. Well, that's just whatever the loss is. Then we've got this general case from A to Z. And then we also want to know from Z to the previous A. Right? From Z to the previous A. So let's say from Z at I to A at I minus 1. What is that? Well, we have this formula that says Z at I right, equals a at I minus 1 times w at I. Well, that's one way to put it. Let's put it a different way. Let's even just look at what the I guess what I want to do is something like this. So z equals a times w. And this is to the I, this is to the I, and this is to the I minus 1. When we're taking the derivative with respect to a, we're going to end up basically with a w. Okay? As we're computing the partial derivative, so partial derivative of L with respect to, let's say, a at I minus 1, this will be the partial derivative of L with respect to z at I times this partial derivative. This partial derivative is actually a matrix. Okay? It is a matrix of partial derivatives with respect to each one of the elements here. If z at I is, for example, has 3 elements in it. Okay? So this is, let's say, z at I. And this is a at I minus 1, and it has 2 elements in it. So from one level, let's make this one be 1 by 3 and 1 by 2. So at this level we have 3, at this level we have 2. What does this weight matrix look like? What's its shape? Going is it 2 by 3 or 3 by 2? Well, one thing we could do is we saying, well, level 3, W3 is 3 by 2 correctly. Okay? So it's going from 3 to 2. When we're taking this derivative, we've got this derivative, which is of what shape in this particular case? It's a 1 by 2. We want, what's this derivative going to be? Of what shape? 1 by what? 2 elements here, so it's a 1 by 2. 3 elements here, so it's going to be a 1 by 3. Because the derivative is going to match the actual value, right? A at 2 is a 1 by 3. So therefore, the derivative with respect to A2 is going to be a 1 by 3. So this is going to be a 1 by 3. Okay? If we're going to multiply by a matrix, this has got to be a 2 by 3. Okay? And that's why the derivative is basically going to be W of I transpose. Because here we're going from 3 to 2, as we're going the forward pass. And then the backward pass, we're going from 2 to 3.
So in this case, B shouldn't make the difference, right? Because we're taking derivative.
Yeah, if we have a plus B, that'll just cancel. Yeah, it'll just go away.
Could you explain the last step to the transpose?
I am explaining to you why it is of that shape.
Right.
And a transpose gives us that shape. We would have to actually go through and look at the individual values to see why it is this is the right value. Okay, but it is the right value, and I'm giving the higher level reasoning for this right now.
Okay.
That's why that is. Okay. So let's go through and actually start some computations. We started here. We have the partial derivative of loss with respect to z4. Now, let's look at z3. I'm sorry. Let's look at, we're here. Why don't we go ahead and figure out what the derivative is with respect to these weights and with respect to the bias. In fact, let's do the bias, because it should be pretty simple. So, it's going to equal the multiplication of all the way up to here, the partial derivative, times the partial derivative from here to the bias. So that's going to be from z4, and then from z4 to b4. Yeah? Yeah.
What do we need to do for the bias?
Well, a bias is one of our parameters, right? We need the gradient in order to update it. That's why we need to go with the bias, because we're going to want to be computing the gradient to every weight and every bias. Well, what is this derivative? One, right? Because it's basically z equals a w plus b. That's constant. Derivative of b is 1. So that's 1. So, actually, that's our answer. Whenever you want the derivative of the bias, it's just the derivative of the z at the same layer. Now let's look at the derivative of the weight matrix. So let's think about this. So it's the derivative of L to what? Z what? 4 times the derivative of Z4 to W4. All right. So again, we have Z equals A. So this is Z4 equals A3 W4 plus B. Yes.
Is your camera picking this up? You know?
Yes. Cameras should be picking this up. So if we take the derivative, the b is going away, right? It's constant. W is a variable that we are taking the derivative with respect to, so a is the one that's kind of left. Okay? So this is going to be approximately a at 3. Okay, why approximately? Because this is these matrix multiplications, and we need to figure out how to get the matrix multiplications to kind of work right. And I'm going to give you a hand-wavy thing right now, okay? Which is to say that this partial derivative should be of the same form as the weight matrix. So we should end up with W4 is, where'd W4 go? W4 is over here, right? W4 is a 2 by 1. So we're going to have to end up as a 2 by 1. So I'm going to just kind of say, let's multiply this by A3 transpose at the front, and this one by A3 transpose. Okay, this is very hand-wavy. Okay, and I'm going to say what we're going to end up with is wanting to multiply this A3 transposed in front of this. Okay, this is on the second page, the third equation, right, that we actually are going to take A3 transpose it, and then multiply that by our loss to Z4. And we'll actually just do this. Let's just try it and see if at least the shapes make sense. Yes?
So when you say approximately A3, you actually mean A3 transpose?
I mean A3 transpose, yes. So A3 transpose is what? I can't, A3, I don't know what it is. Is it 2, 3?
2, 3.
Times this derivative, which is y hat minus y. So I guess we better come up with a value here. So y hat minus y hat is what, 1/2? And y was 0. So it's 1/2. What is it? Is this of the right shape? It is of the same shape as W4, which is good. So that's telling us that our current values are 2, 3, and the gradient is 1, 1.5. So we could, for instance, just multiply by lambda, add it to this. Sorry, subtract it from this. Does that make sense? Where we are, what we've got. So we have the gradient for B4, we have the gradient for W4. And then we just deal with gradients as we've dealt with them before. Throw them in our optimization function. So if we increase this weight, will that increase or decrease the loss function? Increase it because we have a positive gradient. So that means increase the value means it'll increase the loss. Okay? Which is why we're going to be subtracting these. Okay. Let's move on to do A3, so and so on. So, we can get rid of A4 and Z4 because we've done with them. So I'm going to just erase them now. And if we actually end up needing them, I will ask you what they are. So we need to calculate the loss with respect to A3. So we haven't done one of these yet, right? Because we cheated in going to A4, right? That just came from the loss. We combined it with the loss function. So what do? We're going to say we're going to take the loss to Z4, and we're going to multiply that together with G prime of C3. Let's see whether this makes sense. So we have the derivative of Z4 with respect to A3. All right, what am I doing here? So yes, and this one is our weight matrix. Okay? So transposed, because instead of going from 3 to 2, we're going from 2 to 3. So this is going to equal Z4 is equal to 1/2, right? And correct me if I go wrong here. And this is W4 is equal to 2, 3. And we transpose it, so it's going to be 2, 3, which equals 1, 3/2. All right. So we've made it to here. Let's go another step. Z3 equals the derivative with respect to A3 times derivative of A3 with respect to Z3. And here, what's the shape of this? A3. The loss with respect to A3. Shape is 1 by 2. What do we want this to end up? What's the shape of this? So loss with respect to Z3. What's the shape of Z3?
1 by 2.
We got to match that. So that the loss, the derivative of the loss is going to be also 1 by 2. So this is a 1 by 2. This is a 1 by 2. We're going to want this one to be a 1 by 2 as well. So the derivative of A3 with respect to Z3, well, that depends on which function we have, right? In our case, we have a ReLU. So A3 with respect to Z3, let's just think about this. We had something that said A3 equals ReLU of Z3, right? So we're going to basically be doing a ReLU prime of Z3. That is going to be what we're going to have here. Yes?
I'm confused is if we want a 1 by 2 and we know that partial L, partial A3 is a 1 by 2.
We're not going to do a matrix multiplication here.
Oh, okay.
So yeah, I'm going to show you that in just 1 second. We're going to do just a element-wise multiplication.
Okay.
So we're going to say this is equal to 1 by 3/2. And then we introduce some notation. This is just an asterisk in NumPy. Right? It's just a point-wise, element-wise multiplication. And so this is now going to be this derivative. So what's the derivative of ReLU? Right? We know ReLU looks like that. So if it's positive, what's the derivative? And if it's non-positive, what's the derivative? 0. So let's look at Z3. Z3 was equal to 2, 3, right? Yeah.
So just for clarification, at 0, we're saying we're equal to 0?
We're going to, yes, we try not, yes, it's 0. It really, we do have this discontinuity there. So if this is Z3, what's the derivative of Z3? Or of A3 with respect to Z3? It's 1, 1, right? This is non-negative. This is non-negative. Sorry, this is positive, so I just said. So these are going to be 1s. So this is going to be times 1, 1. And this is a Hadamard product, which just means element-wise multiplication. Yes?
Can you explain why we're doing element-wise multiplication here?
So I can explain it in 2 different ways. One is by looking at the shapes of these. We know we have 2 of matching shapes, and we want to end up with a matching shape, so we're not going to want to do a matrix multiply. That's the simplest way to answer it. The more complicated way to answer it is this. we have here A3, right? Which basically has a value here and a value here. This value we want to multiply by this derivative, just by a single value, which is either going to be 1 or 0. And this one we want to multiply a single value, which is a 1 or 0 to get to the derivative here. So we don't have any of these complicated summations and multiplications. We just have a simple one step from here to here, one step completely separately from here to here. Does that help? Okay. Okay. And now we just keep going. All right? I'm not going to keep going all the way because we've shown all the pieces. I've shown how to go from a previous z to this level's a, from this level's a to this level's z, from a z to a w, and from a z to a b. What I would like you guys to do, while it's still fresh in your minds, is do this yourselves. So I have group exercise. You're going to break into 4 groups of 5, no, 4 groups of 4 and 1 group of 5. All right? And you're going to work in your group of 4 or 5 and huddle together and move the tables if you need to. And you have a different neural network, and you are going to do the same sort of thing. I've already provided you, I believe, all the forward propagation stuff you'll need. Okay, so here, I will assign groups for you. Let's see. In the back, 4 and 4. Here in the middle, 4. Here, 4. And you guys, 5. All right? So you're going to have, let's say, 10 or 15 minutes to work on this. And then you are going to have one person from each team present one layer.
Can we just do it like this so it's easier to watch?
Sure, you got it. If you want to Okay, and the tables are on wheels, and the chairs are on wheels. So feel free to just like whip this so you guys are closer together, facing each other. Excellent. We're just trying not to crush it.
Like the full
Do you have the problem? Okay, guys, speak up. Anyone have an extra problem? You guys have 2. Don't cheat. You get 1 per turn. Do you have an extra one too? You guys, would you like a problem? They were hoarding 3. You're welcome. It's going to be much easier actually having a problem with me.
And this was this and that. That also go down to all the points like you start writing down here. It depends on the
Ezra, is one of these you? Which one? Just put your name at the top, please. If you would like to have credit for it, give it back to me. Thank you. Unfortunately, I only did one copy for a group. In retrospect, I can see that might have been a mistake. No? Can we pass that to Leo? Ben, are you Ben Meyer?
So yeah, really
So we have a sigma
this is going to be 0.5 times 4.
Brandon, is this you?
yeah.
All right.
Sorry.
Can you put your name on it and I'll take and give it back to me?
And then similarly,
Okay. Okay, and you guys don't bother with B3 and W3, okay? Just work farther down though. Okay? And you guys don't do B3 or W3. Okay? And you guys don't do B3 or W3. Just zip on down, or B3 or B2 or W2. You're trying to get as fast as you can to B1 and W1. Okay? You guys, as quickly as you can, work your way down to B1 and W1. Don't worry about B2, W2 or B3, W3. Okay? Yeah.
Do you want us to do B2 and W2 then, or?
Yes. Wait. Yes. So you're trying to get your way to B2 and W2. So I do want you to do B2 and W2.
Okay.
so it's going to be 2, 0,
Nolan.
Okay, so now we're on to.
So now?
Yeah, we can do DL.
So it's going to be the commercial derivative of
Alright. And that's just B. I want.
Which is going to be.
Matt, this one's yours.
So just to make sure I'm
Like it's not.
the weights and the biases.
No.
This is the A0, A1, and A2.
But they're labeled. This one's A3. This is A4. It's just not labeled.
Yeah. That is correct.
So like, actually, this derivative is actually going to be great. It's only these ones. So, shit, just screw it.
Wait, no, hold it. Why do we have an A4? This is A1, A2, A3. Right?
A super W.
Oh, it's
Yeah, it's the third one in the. So there's no Z4, it's Z3.
Y minus Y hat is
So it's going to be 4.5.
Do you want
this, right? So what's respect to? Yeah. So that would not be with respect to what?
Because they're also going to be some of them.
Which is,
Wouldn't it be interesting to use first? And then you know that for
we're doing W2.
yeah.
So is it 4.5?
Okay. Remember I said you guys don't do W3 or B3. Work your way on to, skip W3 and B3, and get your way to W2 and B2 as fast as you can. Oh, it's W2? I'm sorry. My mistake. But go in order. So you did layer 3, right? You did layer 3. You did the loss with respect to Z3, right? In order to get the weight 2, you need Z2. In order to know Z2, you need A2. So you're going to need to go to A2, then to Z2, then you could do W2. You can, but don't do it that way. You want to do backwards. So you want to do, think of it as going Z, A, Z, A, Z, A, Z, A. And whenever you want, you can take the Z's and figure out W's and A's. So what do you want? What are you trying to do next? We don't care about W3. Skip it. Yes, A2. That's your next one. Okay. So you guys have, this can't be right. How many layers are in this? 3. That's why we have 3 W's and then layer 1 here. So I will agree that Z3 is that. And throw it in there. Okay. Now you can calculate A2. And will that one be? Yes.
Okay, so matrix right here instead.
Partial Z, partial Z, partial more the whole thing, it is obvious.
And that we
It's cool. It's really good talk. So that's a 3. He didn't use his finger as an eraser. Okay, yes.
We messed up. You guys, we were supposed to
Okay, Z2. What is the You can rip them apart if you like that. Feel free. Oh, is this C2? That's C2. So it's a 1 by 3. So you have a 1 by. Is this a 1 by 3? Yeah. Okay, so that looks good.
Wait, so that's what we're confused. Did you see the W2 is A1 transpose, right?
Yeah. Here's what you want to do is use, if this is your formula, how are you going to be doing it? So from a W is equal to A transpose first, right? We switch the order. We have to switch the order of it. You just need to. Yeah. So the A1 transpose first.
Okay. But then why did you switch the order?
Yeah.
This is,
Well, and you would have known that wouldn't work because it's not a constant. Really, it's 1 by 1, and so you would have failed.
this is a 1 by 4. What is it?
No, that's right. Yeah, we're using it to.
Yes.
Yeah, so now it's partial of A2 over the partial of Z2. So that's
It's like 3 by 4, right? Yes. This is going to be like 0, 0.
and that we what's going to be the matrix that you have up there. Equals the matrix that you have up there.
Yeah, that one or that one. Fake times. Yeah, null matrix multiply. How's it going, guys? If you want to take a blackboard place, feel free. There's one open over there. That would be useful. Can you squeeze it? Okay.
And do we have that?
Okay. I agree. So let's figure out what's going on. So this is Z2. Sorry. DLDZ2. Okay. And this is supposed to be. Okay. So show me A1.
Yes.
Okay. So now we are on.
Okay, so let's look at where's. So Z2
is 4.500. And then this is.
Are you
I think that'll be the same dimensions as W2.
Can you, like, in this order?
Wait, it's W1.
You do two dimensions.
Oh, yeah, this is fine.
Okay.
Because it's a 4 by 1 by a 1 by 3 that matches and gives you a 4 by 3. Why were you confusing me?
Sorry.
You had me confused too. Let me go.
So it's 1, 2, 3,
How's it going, guys? Why are you doing W2? Remember I said, don't do W3, you don't need W3, you don't need B3, you don't need W2. Right? All you need for W1 is 0. And you don't need a W anywhere down. So, skip that one. But it will give you, it would give you a 4 by 3, which is correct. I just wanted to get there because I want among the entire universe, we've got all of them. If that makes sense.
It sounds like
This makes sense.
B2 is equal to what we already calculated. Equal to DLDZ now, right? So B2 that is
Equals.
Let me see the picture.
Correct.
Okay, that looks right. I did, well, I was used to that one. I don't remember what this one looks like. So I just didn't realize the first layer has 4. So that's what you ended up with. That's good.
Value of Z1. It's the value prime of Z1. And Z1 is.
All right, we got 3 more minutes. Yes? Keep going once you've got those down to do the A's, A1s and Z1s.
Yeah.
So this equals
KC.
4.5. It's going to equal DLBZ2, which we already have. So it's just 4.5. What?
Yeah.
So just.
Where'd your negative? Yep, that seems good. Okay, do W1 and B1?
This guy.
In fact, do B1 right now. Oh, you have to do Z first, don't you? We don't have Z.
Oh, you're right. You have to do the relative.
Yeah.
And then
So this is W2. 0. So this is Z2, Z2.
So this is D. Wait.
Right.
Partial C, partial D2, partial A1. It's not the transpose of that matrix, because that's the base. This is the transpose of the matrix.
Times DL.
This is
What is the first transpose?
4.5.
Oh, okay.
5, -1.
All right, and your last one?
And this is 4.5 and this also equals negative 4.50. So this turns into.
Because that's A0, right?
What is the transpose? Z is divided 4, so it's going to be 5 times this, right?
Yeah, 5 times the row.
Which is A0 is 45. 5 times 9 is 45, right? Negative 23.5. 0. Negative 4.5.
All right, here's what I'd like to do. You guys, over here, can I get your attention, please? We're going to stop now. We're going to go through. You guys are first going to take us to W3B3. Okay? So you're not going to just circle it. You're going to take us to it. Run it through. Okay. Everyone, give full attention. Okay.
Okay. So we started with DLDZ3, which is eventually DLDW3. It's going to be DLDZ3 times DZ3W3.
And you don't even have to think of it that way. The way we do backpropagation, we always start the last layer with the Z's. So the A to Z. So.
Yeah, so we started with DLDZ3, which is DLDA3, or which is actually by hat, DA3DC3, and because we have cross-entropy and sigmoid, this is y hat minus y, which is like that. And then so, do you want me to do B3 as well?
Just say it quickly.
So then DLDZ3 is DLDZ3 times.
And it's even just DLDZ3.
Yeah,
you don't even have to do any more. From our little formula right there, it's just DLDZ3.
So that's 0.5.
Except it's actually a matrix. It's an array.
Yes.
Okay.
And then DLDW3 is DLDZ3 DZ3W3, which is, this is actually going to be, which turns into be A2 transpose times 0.5. These are actually flipped. Which turns out to be 2019.
Okay. You guys, can you take us to Z2? Stand up, someone, and take us to Z2. And do we also agree that it's Z3 is 0.5? Yes. All right, Jack, stand up and walk us through this.
What we had originally was the partial L, partial Z3, which we know is going to be the partial L over partial.
We don't have to say, we got it.
Okay.
Because we have Z3 from there. Moving on.
Moving on. So you said you want to take us to A2?
I want you to take us to Z2. Excellent.
Z2, sorry. Okay. Perfect. So,
but in order to get to Z2, you have to do
A2 first.
Go.
So we have partial A2, which is going to be the partial L partial Z3 times partial 3 partial A2. Now we know that this term originally is just going to be the 0.5. Again, it's the array, not the constant. And then we were given the partial Z partial A2 term, which is this 9, -4, -1, 1/3. So we're going to end up as a 1/1 times 1/3, which is a 1/3 output, which is 4.5, -2, -0.5. And then from down here for the, now we have the partial L partial A2, we can go to the partial L partial Z2, which is just going to be the element-wise multiplication between what we have up here, which is the 4.5, -2, -0.5, times, in this case it's going to be the, given that, yeah, it's the relative part, and so from the outputs we have, yeah, it's Z2 is equal to 4, -338, so it's going to be 1, 0, 1, and so we end up with the, this -2 term is going to go to 0, and we end up with a 4.5, 0, -0.5.
Anyone, any arguments on that? You guys have a different value? Okay, good. You guys take us to W2, B2. Can you do up on the board, and if you want to use their, I can give you chalk if you want.
All right.
Okay. Start with B2 because it's so easy.
Okay. We said that DLDB2 is just the same as DLD2. So I don't know where that is.
This one here?
Cool, thank you.
You agree with this
yes.
one? Okay.
That's the one. And then there is DLDW2, which was the transpose of A1, which was 2, 10, 19, and 0.
Oh, yeah, that works.
And then multiply that with this. And we got
a giant array, right?
Yeah. Love it, thank you.
Okay.
Cool.
So we just pull the cake out of the oven. It's done. There it is. Yeah, we don't have to do it. Okay, you guys take us to A1. Let us just stop right now. Stay where you are. A couple of announcements. Someone asked on Piazza for homework solutions and quiz solutions. So I decided that's a good idea. So I now have posted, I don't think I posted homework 5, but I have it printed out. So homework 5 solutions and quiz solutions. I'll post the homework 5 solutions too, so take one of each. All the rest are up there too. I have extra office hours today until about 10 after 4 in the cafe. And then from 5:45 to 7 in my office. So let me write that down. I'll only be about 90 more seconds. So office hours. Today until 4:10 in the cafe. And from 5:45 to 7, I'm going to say 7 plus in my office, because I may be there after 7. For the exam, 1, 8.5 by 11, single-sided, handwritten, set of notes. Okay? On Wednesday, what are we doing? Review, which is being question-driven. So if you don't ask me anything, I'll say nothing. So ask me questions. I highly recommend you know how to do forward propagation and backward propagation. It's definitely something you will want to know for this class.